Welcome back to Advent of Code 2019, day 19. We are 2/3 of the way through. We're into possibly the harder problems. 19 is probably an int code because this one was not, so... hang on. Music a bit loud, let's turn it down a bit. There we go. Okay, let's go. 19. Nice short description. Unsure of the state of Santa's ship, just pouring some copy, you borrowed the tractor beam technology from Triton. Time to test it out. When you're safely away from anything else, you activate the tractor beam, but nothing happens. It's hard to tell whether it's working or if there's nothing to use it on. Fortunately, your ship's drone system can be configured to deploy a drone to specific coordinates and then check whether it's being pulled. There's even an intercode program, your input, that gives you access to the drone system. The program uses two input instructions to request the X and Y position to which the drone should be deployed. Negative numbers are invalid and will confuse the drone. All numbers should be 0 or positive. Then, the program will output whether the drone is stationary or being pulled by something. For example, the coordinate x00 is directly in front of the tractor beam emitter, so the drone control program will always report 1 at that location. So a beam is like a cylindrical, I don't know. Wait, this is in 2D space, right? Yeah. Also, it's a beam. It's a cone. It is important to get a good picture of the beam itself. For example, suppose you scan the 10x10 grid of points closest to the emitter. In this example, the number of points affected by the tractor beam in the 10x10 area closest to the emitter is 27. Hello, DJ. However, you'll need to scan a larger area to understand the shape of the beam. How many points are affected by the tractor beam in the 50x50 area closest to the emitter? So, we don't know where the emitter is, do we? Everything's in the positive quadrant. Oh. No, the emitter is at 0, 0. Or at least... directly in front of the emitter. Okay, yeah, so effectively, emitter is at 0, 0. So we're going 0, 0 up to... 9, 9. Fine. So here we would go 0, 0 up to 49, 49 essentially. Okay, I didn't look at this last statement here. That clears it up. Okay. So it's like 2,500 different cells. Do we want to make 2,500 calls to the encode problem? Probably not, but I don't know. Maybe maybe that's all you do. Because it's going to be like a convex shape. Well, not technically, but convex-ish. So, in theory, you wouldn't need to check every cell. If you know... if you see a hash, and you see another hash, then you know that in the same row or column, every hash between them is a hash. Right? So it is convex in that sense. I don't know what the term is for that type of convexity. Integral convexity. But we might not need to optimize it like to that extent. But It's just something to think about for part 2, maybe. So we just call the encode problem, right? We'll try that first. It might be too slow. In which case we'll need to just find the boundaries. If we find the boundaries, then we just fill in all the rest of the hashes, right? Okay, so let's go. So we've got encode, and just copy in this program. Yeah, this program looks like it might take a while to run. Okay, so 17 was the last encode, so I guess we want this as always. How many points are affected by the tractor beam? So basically... Okay, so... Right, so where do we create the encode? Do it like this. Encode equals... encode program. So... we do... Or, okay, this is the very naive algorithm, but if it works, then this is very quick, part 1. For I in range 50, or j in range 50, we do encode dot put input. So how do we put the inputs? X and Y. X being the J value. J. And then separately we put the I value, which is the Y. And then what we get back is a 1 if it's a hash, 0 if it's stationary. So what we're trying to count is tractor. Let's call them tractor points, I guess. So we do tractor points plus equal output, so that'll be a 0 or 1. So we just it's gonna be a 1 if it's a tractor, so do that. Print tractor points. Let's just print I. I want to see what progress we're making here. Plus equal none type. Ah. Okay, fine. Status equals... Oh, I don't know, cell? I can't think of a good name for that. Cell equals... I wish I originally came up with a better way to handle these nuns, but I guess... it's fine. Alright. If cell is none break. So... wait, why would we ever get none? No, so there's a problem. Yeah, we should never have this. So we put a J, we put an I, and then we get an output. Is that the order of operations? I don't see any issue here. So the most basic case is we are doing 0, 0. Right? 0, 0. Okay, we got something. 0, 1. Ink code terminated successfully. What? Why didn't it go on to 02? What? Code. Get output. So if it's faulty, it would return none. But we would just go on to the next. Alright, just so I'm not going mad here. Let me see this. Don't do anything with. Okay. So yeah, so that works fine. Tractor points plus equal. Code.get output. Why would... Or maybe you only use the program once? Oh. Okay, that was not clear from the description at all, because in the past we've been able to continuously use inputs and outputs. For goodness sake, so... I'm guessing... we have to reset the program every time. That's why it's going to take a long time, but okay. So do that. Let's test that. So do it like that then. 203. Fine, that didn't actually take long. Should just be right then, because I mean, we're just running the program as a black box. Correct? Okay, that was actually, I mean, apart from the fact that I ran into trouble, that was basically the easiest part one ever, because you just call the program and take its output. You can't break it down any further than that. Okay. You aren't sure how oh. Right. Part 2. You aren't sure how large Santa's ship is. You aren't even sure if you'll need to use this thing on Santa's ship, but it doesn't hurt to be prepared. You figure Santa's ship might fit in a 100 by 100 square. Beam gets wider as it travels away from the emitter. You'll need to be a minimum distance away to fit a square of that size into the beam fully. Don't rotate the square, it should be aligned to the same axes as the drone grid. For example, suppose you have the following tractor beam readings. In this example, the 10 by 10 square closest to the emitter that fits entirely within the tractor beam is marked 0. Within it, the point closest to the emitter is there. Okay. Find the 100 by 100 square closest to the emitter that fits entirely within the tractor beam. Within that square, find the point closest to the emitter. So, it's a geometry thing. We're just trying to find the square that closely fits. Okay. And then from that point on, it was just do that. Okay. So would we not start? It's 100 by 100. So like start with the square being here, and we evaluate it, and then work out. Alright, so if the bottom left corner and the top right corner are in the beam, then that means the whole square's in the beam, right? So to try a square, we test the top right and the bottom left. If they are both hashes, and the top left, of course, is a hash as well, then we're good. So if they aren't, then we have to perturb the square based on what we're seeing. So if we don't actually know what the angle is that it comes out at, so we can't make any assumptions. So I reckon we start with the square just right at the start. So 100 by 100 square just sitting right here. we evaluate its top left, its top right, its bottom left. And if it's like top left is hash, then we okay, we're sort of doing a breadth first search. Well, not really a breadth first search. A search where we either move right, down, or down right, depending on what we see. Okay. So, how does this work? I mean, wouldn't it be easier just to start from a square that does fit and then push it up and left? Maybe that's the better way. So when would that happen? Like... So for a 10 by 10 square, it happened at 2520. What would the numbers generally be? So let's just try some stuff then. So let's make a helper method here. So define is tractor ij. So we just, on the fly, we make a fresh int code. We do this basically. Int code, put j, put I, return bool of that, basically. Okay. So if we put this one up here, then it's just tractor points plus equal int is tractor ij. Alright, so does that still give us the same answer? 203? Yeah, okay. So, I feel like this problem might actually be very easy, I don't know. Alright, so part 2. First, let's manually find a place. I can't be bothered to programmatically use binary exponential increasing or whatever to find the point. Let's just manually find it, it's easy enough. So let's just find a point where we know the square fits. So, define get corners for a given I and j. So top left is going to be just I and j. So we're saying that it's centered on that, well, it's cornered on that point. So top left will be this. Bottom left equals this. Plus, so square size equals 100. So this will be work for the example if we tweak this one. Okay. So top left, bottom left will be I plus 100. Oh, plus square size. Just be completely explicit here. Square width j, and this, and then we'll do top right equals so this will be that, and then return top left, bottom left, top right. So actually we can just do this for I in and get arbitrary bit. just try each x, I, and j until we find one. I don't know how long this will run. So for I in count, or j in count, we need itertools.count. If get corners I, j equals true, true, true. I think this might take too long, but let's try it. Print ij, well, I don't know. Return ij. Print ij. Let's try running that. 4949. So it's saying a square fits in 4949. Wait, isn't that the answer then? Because there couldn't possibly be a square at an earlier I value, or we would have found it. Oh, wait. Not quite true. Right, let me think. So for a given row, We are starting from j equals 0 and just increasing up to that same point. So all we know is there is no square to the left of us that would work, but there could be one above us. So let's do this. We'll say while true. Now that we have a square which fits. Now 49, 49. Does that make sense? Yes, because... Does it? Why is it suspiciously also the final point of this? Let me try different, like, I don't know, 50. What? Oh, take that out. Okay, print ij. Wait, what? No. Oh, that's why. Because I wasn't printing the result of this. That was stupid. Alright, print. Get arbitrary fit. Okay. I was just printing what I and j were left over from this for loop before. Alright, now try running it. It's probably going to take forever now. Just trying to find some place. What I value did we get up to? What? Oh. We're going off in the infinity for j. So we're going in squares. So this should be range up to the matching value of I. So it's 1. Okay, now do it. So it shouldn't actually take that long until we find one. Shouldn't it? I mean, the cone is spreading out a bit, so... We can actually... So we're redoing values often. Let's say we just... Can we get up... Oh, we could use memwise. So let's say, get corners. So basically we say define square fits or give an I and j. I mean, do we care about getting the corners? Let's just say square fits return say if not top left return false. That cuts out having to do another if not bottom left. Or should we just... Come on, let's just make this a bit cleaner. If not is tractor return false. Or just say return is tractor I, and because this is all short circuits, so this is exactly what we want. And that and that. Okay, that's it. Just do that. Because it will, once it gets a false, it won't do the remaining ones. So, and we can memwise. Memwise? Is that the right one? How'd you do it? Func tools, memwise, something or other. Func tools cache. I just want to see an example. Got it. Alright, we're using this. Like that. And we need to import... Or, no. That. So now it should be faster, right? So if square foot, so it won't keep, it will only okay, let's try now. So even if we're going to, well, how wide is this beam? Like if we're going to the thousands, we should find one, right? So now it's slowing down a bit because it's wasting time trying all those previous values. You could write this in a way, in a snake-like way that would actually not keep reusing values, but I'm too lazy to do that. Let's try. So we should find one before we even get to like 1,000, shouldn't we? I mean, it's... I don't know what this beam looks like. It would be weird if we didn't. Okay, there we go. 534 443. Then what? Now, because of the process we did, I'm not sure if it's actually the top leftmost, because we all... I mean... It is the leftmost, because we went across. But is it necessarily the topmost? Could there be one above it? There's definitely not one that's up left of it, because we would have found it. Could there be one that's up? Yes, there could. Alright, so let's just do this cleanup thing. We say while true. If... So, okay, so we got ij equals get arbitrary bit. Fitting square bound at j. Okay, now we're just trying to optimize by pushing it up and left until we find the right spot. So, while true. We just keep... I'm not sure. We're making some geometrical assumptions here. Like, there's not necessarily a neighboring square that fits. It could be that there's an earlier square which fits. Alright, we'll test this, and if it doesn't work, we might have to, Oh, no, but we would have found it. So... what am I trying to do here, then? We don't need to do this while true thing. It's literally... we just need to check above. So... if... square fits... for I minus 1 j... then we just do I minus equal 1. Because that's the only place we don't know for sure doesn't fit. And then are we done? Okay, stop printing the eyes. Or, I don't know. So once we've done all that, we've got the leftmost, haven't we? So then what? Just print... let's have a look. So they wanted us to do... 10,000 J... so it'd be 10,000 times J plus Y. But plus I. And that's it. Alright, let's just try that now. So where did we find it? Around 600 or something. Okay. So it's a bit hacky. I don't think it's possible for there to be a... unless I've made something really wrong about this assumption, but I think it's sort of integrally convex, in which case, as long as you increase this square outwards, the first time you find a fitting square, you only have to check left or up, or left up. And because of the way we did this process, we already covered the left and the left up, so you just have to check one space up, and then you're done. Like, otherwise you would have found... ooh, wait. Technically, you could keep going up a few more spaces, so this should actually be a while loop. Should we do this one more time? Let's say... while square fits I minus 1 j I minus equal 1, because you actually could, because of the weird, if it was a weird angle, you could actually keep going up a bit more. You know what, I'm just going to write this completely explicitly. I don't know, I can't make any assumptions here. Let's say, while true. Okay, we check up, we check left, we check up left. I don't want to rule out anything, so let's check up left. If square fits I minus 1, j minus 1, then I minus equal 1, j minus equal 1, continue. If square fits I minus 1, let me go like that. If square fits j minus 1, we do like this. So if those three don't resolve and we get this far, then we break. And I and j should be on the final value. Alright, let's try it now. So this one gave us 5, 3, 4, 4, 4, 3, and... Oh, that's the answer then. Because there was nothing above it. Okay, but this is 100% correct. Okay, so let's see. 4, 4, 3, 5, 3, 4. That took a bit to run. Yeah, because it's like... Ideally, if you knew roughly what angle the beam was coming out, you wouldn't keep trying all the left and up values of the increasingly sized square. You would just stick within the beam. But I can't be bothered to do that, so basically I'm covering I'm covering all these spaces out here, which you don't need to try. You just need to stick within the beam, because you see where the beam is as you're going along. So yeah, it's a bit wasteful. You could even use binary search to cut out some work here. Good old brute force. Yeah, it's almost brute force. If I were to... Well, it is. It is the most brute forcing method. Like, what would be even less optimized than that? Because you can't just go infinitely to the right, clearly, because you'll never end. So the most brute forcing thing you could do, which would technically terminate, would be just to increase squares off searches, and then just... Oh, the true brute force would be not to use cache. We're using cache here. So recompute the values you tried before over and over again. Alright, let's try that. It's not correct. It's too low? How could it be too low? Because that means... What does that mean? Okay, so it's not there. So should we test this method on the example? But I have a feeling it will just work on the example, but not on the big one, because something about the weird shape of the beam. Oh, we can't test it on the example because they haven't given us a code that generates it. So all we know is that... Did you reverse X and Y? At what point? So we're using rows, I to be rows and J's to be columns. So this stuff, it doesn't matter as long as these I's match these I's and these J's. So the only point at which it would matter would be at the end when we output that. So it's 10,000 times J, which is the X value. That's I, which is the Y value. When the other place where it would matter would be when we're calling the program. So it would be is tractor actually we should cache is tractor, not square fits. Well, we could cache square fits as well. I don't know. We don't need to. That's actually probably more efficient. Oh my god, we're still using square width 50. Because I was testing 50 for some dumb reason. Oh my god, so that's why. It's actually supposed to be 100. So that means it'd be much further out. Well, okay. Let's try it then. It's gonna be take much longer now. Because we've doubled the width. Is it realistic? So, for 50, we found it at about 500. So it was like 10 times. So if that pattern, if that pattern continues, because it's sort of like the beam is linearly spreading out, so then for 100, we should expect around 1,000, maybe. So at the rate that we're going, it might be okay, but it's as it spreads out, it takes longer and longer to calculate. But so we should be using exponentiation to skip outwards, but to find a point that fits. I can even do it by hand. I can literally just try 2,000 but 2,000. And it will probably fit. And then from that point, we just go left and up and down. Can we reason out a point that we know will fit for sure? No, because we don't know what the beam looks like. It could be at a weird angle. But if it's... I will just let this run. Like, in theory, it could be at a really shallow angle, at any amount of shallowness. So we can't, even though we know it probably isn't, we shouldn't make that sort of assumption. So we're getting into the 1,000 territory here, that we might find the point. But we're caching the values of the int code so that it only ever needs to be run once on each value. See, like, if I were to just put a count step equals 10, so that we're only counting every 10, that would actually get there quicker. And then we'll just iron it out by... Step equals 10? Should I just change that, or... Because that will reduce computation by, like, a factor of 100, because we were going... Instead of checking... Oh, there we go. Is that the answer? I mean, I feel like once we found a value, it should just be correct, because if it wasn't correct, it's too high now? Oh my god. Alright, fine. So then that means... we have a weird situation where... Alright, I think this assumption here is incorrect. Because the beam could be at a weird angle, you don't need to... you can't just try I-1, J-1. You actually have to try every possible I and J less than... because... so really, what we should be doing is... the moment we found a fit... we need to rerun this process, but only... Alright, first, before we do anything else, let's try and... ooh, I haven't got the thing open. Let's just try step equals 10. And here we try... okay, just try like that for now. Okay, and then here we try go from 0 up to and including I in blocks of 10. All right, try that. 8861068. Okay. That proves that... so we just found a bigger number now. So we found a square which fits. Now... I see. So basically we have to try every I and J value less than this. Wait, what exactly are we minimizing here? I think I've not paid attention to that. It's not necessarily... the point closest to the emitter. Oh. Yeah, but what do they mean by closest to the emitter? Like Euclidean distance? Probably the corner that doesn't touch the beam edges. Yeah, but I mean, what is the measure of closeness? I guess they mean Euclidean distance. So the hypotenuse, square root of a squared plus b squared or whatever. I'm not actually calculating that. I'm just sort of... what was I basing it on? I wasn't actually basing it on anything sensible at all. I was just saying, okay, if I find a square up left or up left, then I switch to that one. But that's not enough. We need to actually find the square which minimizes the hypotenuse distance. Okay, so I think what we really need to do now is... So we found a fit. And from that point... so basically, if we were to find a point which fits, we would need to try all points on a radius in like in a circular arc. Hang on, I need to be showing the screen. So if we found this point here, that fits. The only way we can convince ourselves that there's nothing closer is to go in a radial pattern, like this, like forming a circle. And checking that all those points don't fit. Alright, this is harder than I realized. Okay. I mean, we haven't wasted time. We have a method now which gets an arbitrary starting point. We just need to beat that point. So now that we have that point, how do we... So, could we find the two corners that touch the edge of the beam and just add, subtract from ij to get the closest point? Well, we won't necessarily have two corners that are touching the edge of the beam simultaneously. That won't always be the case. Yeah, the example is very simplified. This example really doesn't really illustrate what it might look like. I think we might have a really wonky angle for this beam. Let's just write the brute force approach now. So we know that the best distance we've found so far is this I and this j. Okay. So I'm going to take this out for now. So if we run this, it runs pretty quickly. And we found a square. We don't need to do this one here. And we've pushed it up and left a bit until it's kind of it's wedged in. It can't be moved left one space, up one space, or up left. But it could be moved, I don't know, like a knight's move, for example. We don't know that it could be moved 1 up and 3 to the left. We don't know that. All we know is we've wedged it in quite well. So, oh, right, okay. So we found an arbitrary fit. So now just do brute force and let's see how fast it runs. We just want to basically try every x and y value for which the radius is, for which the distance is less than or equal to. Okay, so square distance equals, so it's going to be I times I plus j times j. That is the distance from the emitter. Damn it, stop. Okay, change that to that to that. For goodness sake, why does the IDE keep adding stuff? There, okay. So we've got that square distance. Now we basically just have to try every I and j value. So try every I and j value on the arc. How do we do that again? We need so we're saying while true. So we're gonna try see best square distance equals this. Or just say this for now. So we go for I in range so it's going to be up to and including math dot square root of best square distance plus 1. So that's the absolute maximum value of I we can allow, because anything bigger than that, it's guaranteed to have a further square distance. Or j in range, so it'll be so remainder equals s square distance minus I times I. So that's what's left for j to use. So then we have to go for j in range, so it'll be that remainder j. So these are all the i's and j's we can try, for which we know that it won't exceed. Well, we know we've covered all the points that could possibly be strictly less than or equal to this square distance, or less than. So for each of these I, j values, if square fits for this I and j. Also, we need new letters because we're overriding. We need to keep I and j. So let's say for A and B, if square fits, okay, so this is a fit. If, and if it's a better fit, A times A plus B times B is less than their squared distance. We've now found a new values of I, j. And then we have to do this hacky thing. We have to say we could make this a method and say define get better fit I, j. Okay, so we say square distance equals I times I plus j times j. Okay, and then just do this all again, but say A and range method, blah, 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 so just use that. Remainder equals that, minus A times A for B in range. Square. So we do if square fits AB, then return AB. Okay. And if we get this far, we found the best possible. Okay. Now, while true, better fit equals get better fit of I, j. If better fit is none, we've proven there's nothing better because we've tried the maximum possible radius. If I've done that calculation correct, I don't know. So then say better fit is none, then break, and then we've actually got the answer. Otherwise, we say I, j is replaced by whatever we found here. Okay, so we found a fit. So fitting square found that with square dist. Let's just have a sense for how fast this is decreasing. Okay, and then we do this, and if we... Let's do that. And fitting square found at ij with square distance I. Okay, let's see if it decreases. That's along the right tracks if it is. Okay, so we find a fit, and now we run the circle algorithm and just check. It's gonna take forever though. Well, it shouldn't, because it's trying the square root of... Hang on, have I got this calculation correct? Square distance equals I times I plus j times j. So instead of the square now going up to ij, it's now curving it round into a quarter circle. So that would be bigger, but it shouldn't be much bigger, so... But it would take a while because it has to... Because we were skipping every 10, weren't we? So we should try and... Put some metrics here, say... There's actually some shortcuts we can do here. We can say if it's not a hash, we should just stop, right? Because, wait, no. No. So we're starting with a equals 0 and b going kind of like down. So we could say the moment b hits a non-hash, we should just stop, break out of this one. If not, is tractor. Just break out of that. Okay, try again. Math domain error, what? Math dot square root of remainder. Math domain error. Math dot seal of maths. This has probably become negative somehow, I don't know. Square distance. Oh, because of this weird rounding. Okay, just say max of that and 0. I mean, I thought this would still work because this will just be... Okay, just try. Eight 8861068. What? 8861068. Isn't that what we tried? What did they say? It was too high or too low? They said it was too high, so we've found this. And we didn't find anything lower, even though we did before. So this method is not working. Oh! Maybe this has a better square distance than the one we found before. Oh, of course. 886. Okay, let's try this answer then. No, but this is suspicious because... Okay, anyway. $886,1068. It's not correct, it's too high. Closest to the emitter. So they do mean Euclidean distance, don't they? Okay, just stop printing this for now. Stop printing this. So we get an arbitrary fit. Okay, let me... What is that arbitrary fit? I want to see which one is better. Okay. So we later... So after pushing it, squashing it up, we get something with a smaller square distance. Good. So this so far is a point, which is of this distance to the origin. And the emitter is 0, 0, right? They don't actually say. They say in front. I guess. X equals 25, y equals 20. So the top left is 0, 0, is it? Yeah. Also, I think we made a mistake. We're not allowed to do this one here. Let's take that out. This will actually make it run slower, but I guess it's supposed to. Alright, why is it taking so long? Let's have a look at this. I guess we need to be doing some sort of simplifying here. It doesn't even reach... Oh, something's definitely wrong here then. Math.ceil, math.square root of a remainder. Oh, then it got to 100. It just takes forever to try that many values. I suppose that is actually to be expected. I can see how you can all speed this all up by having binary searches, or I don't know. I've kind of stuck with the brute forcey approach, and now that's taking me in circles. Unless there's a quick hack I can do to speed it up, maybe we need to think about. Well, once we find the hashes, so okay, for a given a value, once we find the hashes, then after that, the moment we stop, we go back to the non-hashes, we just need to break out of this loop, don't we? There's no point trying them. So let's say here, prev equals, let's say, false. All right. We can say prev equals is tractor, whatever this is. So at this point, if we're at a non-tractor and prev was a tractor, then we can break. There's no point trying any more below because it's all going to be non-fits. Alright, let's try that now. So that will reduce the amount of B's we try. We could do the same for A. Let's try that. So A, okay, so prev A equals false. A in range, blah, 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 blah. So we say prev A equals I don't know. Alright, leave that out for now. Yeah, no, this doesn't make sense. Okay, just stick with the prev just for the B's. Alright, run that now. That'll avoid computing too many B's. I don't know. Maybe the better way is not to start from an arbitrary fit, but just do like increasing radius until we find the radius for which well, this is going faster now, so this might actually work. don't find a better fit, we break out of this. So we should find a better fit. They're saying that what we submitted here was too high, which means there is a better... Well, it doesn't mean anything because it's saying that the 10,000 times j plus I is too high. But we know that the square distance is probably too high because we know that this particular square does fit. They haven't given us a small test case to play with here, so it's quite hard to do anything here. Let's see, like, make your own, I don't know. 900? So... that number... square root of that, what is it? (1387). So we will go up to 1387 before we stop this process here. Hopefully we find something. Oh, we're finding better... What the... Oh, I see. Hang on, stop. 1911785. 1064883. And that's better than... We haven't checked that we improved. Alright, one. Alright, so here we say return B. If square fits and A times A is plus B times B is strictly less than this, we return that. It seems we're just returning IJ over and over again. So it looks like that might be the answer, 1064883. I mean, we could just test that now. So we do 10,000. So it's going to be 883. That might be the answer, because we're now not because it's in the loop, it's not finding anything better. And it's cached all the values from before, so it doesn't need to do all the computations again. That's why it goes quick the second and third times. So let's just try it. So we just need to manually enter this. So it's going to be 883. And 1064. It's wrong? 883, 1064. Oh, because I bugged it. Okay, fine. So we can now just run this using this newfound value. In fact, we could just override what we found before. Just say ij equals 1064 883. Okay, and then just carry on from there. So now it's trying to find a better one than this. And because it's caching all these square fits values, the next time it does this, it shouldn't take anywhere as long. It would just be like 1,000 by 1,000, so... And this is going reasonably quickly as well, so... Best we found so far. Alright, well this is very brute forcey. What would you actually do? You would go in and... If you found a value which fits, and is in the beam, I suppose you would find the boundaries of the beam and actually decrease your radius but stay within the beam. It's a weird geometrical thing, but you could do something like that. Alternatively, you just never leave the beam. You start from 0, 0, and you just stay within the beam, like the of increasing radius. Oh, you can do a binary search. You can say, okay, for a given value r, radius, we just find all the points which are on the arc, which stays within the beam, but is radius r away. And that's just a linear number of points, right? So you can just sort of binary search, keep going higher and lower until you find the perfect r. Something like that, I don't know. Let's see if this brute force approach works then. Alright, I thought this was gonna be easier than what it's turned out to be, I guess. I want to see a picture of what this beam looks like, because I think the geometry is just really awkward. Going up to 1387. Alright. Oh, I haven't got it on the thing. Okay, it's just running. I mean, there was nothing interesting to see there. It'll go up to 1387 at most. And if it finishes there, either way, if it needs to do this process again, it's going to be quick because it's all going to be cached for the square fit values, so it won't take anywhere near as long. Yeah, I don't know what the actual best way to do this is. I would think the what I said about the binary search to find the perfect radius would be actually the sensible approach. Because then, once you've got the arc, (886.1068), 883.1064. Damn it, we haven't found anything better than that. 883.1064. That's what we tried. So what have we found so far? We found that for this row, this column, so that's the y value, that's the x value. We've confirmed that that square fits. And then when we run this, we're brute forcing all things with a lower radius than that. So I can't see any way this could fail now. Unless... Okay, just comment out this for now. Square fits. Should be true. If it's false, then we got an issue here. Also, why don't we also memorize this one as well? Can't hurt, right? Is this definitely convex in this sense? It must be, otherwise it'd be really weird. Yeah. So we only have to check these corners, right? That assumption is what we've been assuming all along. Fitting square, found it. Yeah, okay, that's part one. Yeah, so 1064883 fits. We've confirmed that. So what's the problem then? So we're doing square distance equals I times I plus j times j. Okay. For a in range up to the square root of square distance and add one, just is this we're doing a range of a float, I don't know. Can we just int of that? Also +2 just in case. I don't know what exactly is the right place. Int of that. +2 just to be extra safe. Alright, try that. I don't know. So a up to that. Remainder equals, so your square distance minus a times a. And if it's negative for some reason, then why would it ever be negative? Okay, so then b, taking that remainder, letting b range up to and including that. What about this prev thing? Should we just take this out again? So if we get to a non-tractor, and the one to the left was a tractor, then we should stop increasing B because we're outside of the beam. So yeah. Move on to the next A. If square fits A, B, and A times A is strictly less than the square distance, return AB, else return none. We'll see what's wrong with this. Should we take out this preve thing? I don't know if I trust this. Okay, just do the full lot. This is gonna take ages now. Maybe I should just try this other approach, like increase radius until $100. So as we increase A, the number of B's we need to check would decrease. So this took a long time, but as we go to 200, 300 and so on, it should get faster and faster. Let's just let it run then. And if this fails, then... I mean, this is the amount of work we need to do. We don't need to do any more work than this. Because we've found a point which fits, the square fits, and it has a certain square distance. So if we try every possible point with a lower square distance than this, and none of them have a square fit, then we've proven, haven't we, that this is the answer. So if we're still failing here, it can only be a small hiccup in the logic or the calculations here, but the amount of work we do can never be more than that. Like, that is the proof, or that there is nothing better. Right? So there could be something wrong with this formula, or... Fitting square found... Wait, what? Why have we got that? Where was that from? Fitting... Oh yeah, because of this didn't happen. Okay. Just take that out. We have no way of testing any of this, so it could be that there's just a mistake somewhere up here. Is tractor ij, is tractor I plus square root is 100. Is tractor. Get up. So if we were to... Yeah, and we're caching it. That's correct. And you're caching this, that's correct. And a times a plus b times b is strictly less than square distance. Because we've gone +2, so we might actually end up doing I and j again. So there's nothing. It should just work. So I don't know what else could be the problem. And then it's 10,000x. And we take the top left point of the square. So within the square, the point that's closest to the emitter must be the top left. It can't be any other point, so that's fine. That's not a problem. Yeah, we're not even breaking out here, because I don't know if that logic is correct. It's a bit... So it's literally just double for loop. Try every possible A's and B's. Damn it, why? 883-1064. No, it's annoying because they don't... How do we test this? We'd have to write our own override int code for the program. And we find this value itself within that radius. So the fact that it's not missing points, it is actually finding them if the square fits. I think that some core assumption we've made just doesn't hold, like 2, 3, 4, 5, 6, 7, 8, 9, 10. So there should be 10 spaces across, 10 spaces down, if it's 10 by 10. If it's 100 by 100. Oh my god. Wait. Oh my god. Oh no. Oh no, 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 no. I think I missed a -1 somewhere. I think. Square fits. This should be -1 here. Hang on, let me think. So if it's a square of width 2, top left corner, the top right corner will be the top left corner +1. Oh my god. I thought this over several times and I reasoned that what I wrote was correct. But it wasn't. So literally just -1, -1 there. Now what? So we try this same value because the 100 by 100 fits. Let's see what happens. So what's going to happen now? It's going to... Hang on, stop this. Let's do this thing again. Get an arbitrary fit because we'll probably get one much earlier. Don't override it here. We don't need that. Alright. So... Oh my god. Okay. Okay, so we found a much earlier one. Good. And that could just be the answer. If the geometry is actually just really nice, but we're going to try all the smaller radii and see. But this shouldn't take long to run now because... Well, no, it would take the same amount of time every time, but we have actually found a closer point. God, this is just a -1. But I'm sure I thought that over and over in my head. So yeah, if it's a square of 2 by 2 square, then the top right corner would be the top left corner +1, not +2. So it'd be plus width -1. Oh, that's what happens when you don't have any easy test case. That you're supposed to write your own test cases. That would be the proper practice. But I'm too lazy to do the proper practice. Alright, we'll just let this run and this should work now. Like if that was the only problem. And this doesn't find a better one. Because of the integral convexity, I think like this process of going up or left or up left should actually just give the answer. Like I can't imagine, unless it's a really obscure angle of beam, I can't imagine that there is a situation where there is a square which fits somewhere closer, but for some reason going up or up left doesn't get you closer. It doesn't get you a square which fits. Like, what would that even look like? I don't think that can really happen. But any beam which is horizontally convex or vertically convex with each slice. Alright, we'll just let this run and see. Oh, what a mess. So yeah. I could just cut corners and just test this now. We'll do it properly. We'll exhaust this just to prove mathematically that there's nothing closer. So dumb. That mistake would have been caught immediately if we had a test case. I know they want us to write our own, but I would have liked it if they just provided one. I mean, you could just write your own dummy int code, which isn't actually an int code. It just returns whatever is in this diagram that they've shown us on the website. But if it still doesn't work at this point, I guess I'll have to. So we just have to write a... I mean, it's not hard. Just copy and paste that example in. Write a program which returns true or false, which are those values. What's the term that you use? Mock. Basically, we're mocking int code. So we're writing a fake int code which returns ones or zeros based on what we're seeing in this grid. Although it wouldn't quite... I don't know. How long have I been on this one? 2 hours. Not terrible, but I'm sure we could have cut out a whole hour there. If I got that -1 in there from the start. Getting there. Come on, 900. So what would be the... Oh, I don't even want to think about what the optimal way or the fast way of doing this is. I just want to get this done and end the stream. I'm sure you could do some sort of binary search or... Yeah, find. So you can easily find... Okay, we used a process to find a square which fits. So we've got an upper bound on the radius. And now just do binary search in that radius. For each value of each radius you try, you just try a little arc within the beam somehow. Maybe a little error bars left and right. Try all the points. I don't know, something like that. You could make it work. Probably not too hard to code as well. You could also just do some sort of brute force search. No, some sort of breadth first search from the starting point, which you know is a hash, where your neighbors are only ever hashes, and that will actually let you search through. Oh my god, that would work. And that'll probably be better than this. So you'd actually do a flood fill, where you're staying within the beam. And as soon as you find a fit, you just go a little bit further to confirm that there's nothing. I mean, that's still order of magnitude, still order of operations, kind of the same as this, but it's faster because it's not covering all those things which are outside the beam. Yeah, that's probably much better than what I did. Alright, moment of truth. Correct. Oh dear, I made a little mess of this. Lessons learned, which I'm probably not going to obey next time. Test. What are the lessons learned that we're not going to follow? Compartmentalize and test your individual methods before moving on. Test against the test example even if they haven't given an explicit test example. Just write your own mock to replicate that. We're not going to... Who are we kidding? We're not going to be proper programmers. Alright. That's it for 19. We can take a sneak peek at 20. It's not going to be an int code. Donut. Portals. Now we're thinking with portals. It's pathfinding. How many steps to get from something to something? It looks like it's a maze, but you're trying to get to this space here. Cool. Seems interesting. I might do one of these tomorrow, and if I don't, then it might be a few days before I get back to this, so... In the meantime, I need to actually upload the 17 and 18 to YouTube. Okay. That was problem 19. So we're in the final 5, the final week of pre-Christmas December. Okay, see you next time. Bye-bye.